Good morning, everyone. Thanks for coming today. My name's Gus Merwin, or since I'm in a suit, most people call me Augustus. I'm a graduate student, PhD in material science and engineering, and today I'm going to talk about thorium as a fuel for advanced nuclear reactors. My background is in physics, and most of the common thing in physics is to study ideal scenarios, and then sell it to engineers so you guys can make something useful out of it. So today my goal is to present the scientifically perfect part of thorium that makes it such an ideal energy source. So then hopefully you guys can turn around and figure out all the political and economic implications in order to sell it. So I'd like to go over a brief overview of what a perfect energy source would look like. Ideally, it would have little to no emissions or byproducts, things like hydrocarbons that go in and cause global warming, or even nuclear waste that lasts for 10,000 years as a radiotoxic particle. You'd also need a quasi-unlimited supply of this. For instance, hydroelectric power fits the first criteria, but there's a limited amount of it, so you can't continue to run more and more people's society on it. It has to be passively safe in order to be developed across the world and not cause large-scale harm. Things like coal power or natural gas that can explode, and also nuclear reactors, so we don't want Chernobyls happening all the time. It has to be economically competitive in order for the industry to buy it, in order for it to spread and become viable across the globe. And it has to be a proven technology. As a scientist, we can't look around all days at things that look really good on paper, like nuclear fusion or solar cells that have 50% efficiency. It has to be something that we can sell today as a real technology. So unfortunately, this basically rules out all of our known energy resources. Nothing, at least that I'm aware of, fits all these categories. And I'd like to spend the next 10 minutes or so telling you about how thorium fits into these categories. So the first category is emissions and byproducts, what happens while you burn fission or thorium and what comes out of it. In order to do this, I need to give just a brief background on nuclear fission. Current nuclear power comes from burning uranium-235 in a ceramic as our fuel enriched to 5% of 235. And then it burns and you're left with two fission fragments somewhere in the middle of the periodic table. And that's kind of the baseline, as fast overview as I can give of classic nuclear power. The problem with current nuclear power is that uranium, the fissile isotope inside of uranium-235, makes up only 0.711% of natural uranium. So then you have to enrich it to 5%, which is a very proliferant process. It's really scary to go into bad hands. And the problem is that you're left with 95% of your fuel is irradiated uranium-238. And as this diagram on the right shows, uranium-238 can absorb a neutron and become transuranic elements, everything with Z greater than 92. And these are the really nasty guys that you have to store in Yucca Mountain for hundreds of thousands of years. As you can see, plutonium-239 is a weapons-grade material, so you have to keep it under very close guards, and has a half-life of 10 to the 4th years. Nobody, even myself, an optimist about nuclear power, can say I can design a system to watch it for 10 to the 4th years. Frankly, I think it's kind of insane. So there is an alternative. Thorium only has one naturally occurring isotope, thorium-232. This is the fundamental difference between thorium and uranium. So 100% of thorium will go through the following process when it's hit with a thermal neutron. Becomes thorium-233 and then goes through successive beta decays. Through protactinium becomes uranium-233, which then fissions and gives you your energy. Thus, 100% of the amount of thorium you farm and put into your reactor can be burned. You aren't left with a large portion of it. So the bottom line of that is the fact that you go from the top blue curve, which is current nuclear fuel, which is the graph of radiotoxicity as a function of time of the fuel that comes out of the reactor. And you can see it doesn't get safe to that darker line of normal uranium toxicity until roughly 1 million years. However, if you're only left with fission products, it's safe within about 300. That is something I can definitely design a Yucca Mountain or a repository for. With well-known technology, we can do that. Oh, sorry, I pushed too many buttons. The next bullet point I'd like to discuss is fuel supply. We want to make sure we have enough of this for everybody to have an equal share for the next long period of time. It's a fact that because there's only one fissile isotope, or one fertile isotope, pure thorium, 100% of it can be burned. Only 100 grams of it can fuel the amount of energy that the average American consumes in their entire life, including transportation. And it's relatively benign. It can be held in your hand. How much thorium is there across the globe? Literally mind-boggling amounts. This roughly estimates to, I think it's 10 trillion human lives at the American standard of life, roughly thousands of years of energy at the current rate of consumption of energy, which is slightly grotesque. Basically, we have plenty of known reserves of thorium. It's a pretty easy argument. Safety is the next one. Safety for nuclear power is a big scare for people, a lot of people in Nevada especially, because we have a strong fear of nuclear weapons. This gets slightly more technical. I have to give you a brief overview of the classic thorium reactor. It's a molten salt fueled reactor, so the fuel itself is actually a liquid that flows through this reactor and flows through the core. There's two inherently safe parts about this reactor. The first is the fact that because the fuel is a liquid, it has a large thermal coefficient of expansion, so the hotter your reactor gets, the less fuel there is in the core, and the reactor cools down. Seems pretty safe and straightforward. The second one is what's called a freeze plug at the bottom of the reactor there. It's an actively cooled part of the salt over a cavity, and if the reactor gets too hot or something goes wrong, the fan is not able to cool that salt anymore because it's getting too hot, and the fuel drains out of the core into controlled safety tanks that have neutron absorbers, and the reactor shuts down immediately. Two passively safe mechanisms that require no external involvement, which were the problems in classic nuclear power. Nuclear weapons, you can technically make a nuclear weapon out of uranium-233. This picture was actually taken at the Nevada test site. However, nobody has made a bomb specifically out of 233. Even this image was taken with a bomb that's boosted with 233, but it's still a plutonium-based bomb. The reason you have to do that is because thorium-232 is an inevitable neutron poison. It makes it really hard to go critical. And the decay of it gives such a strong gamma ray that it destroys all your chemical, explosive, and electronics. Basically, it makes it really hard to build a bomb out of. Economic competitiveness is a big part. In order to sell it, you have to make somebody want to buy this and have governments go for it. I'm going to take it as a given that current uranium fission is economically competitive. There's 2 reactors being built in the United States on multi-billion-dollar scales, and many applications for more. I believe there's 10 currently pending at the Nuclear Regulatory Commission. So I'm going to take that as justification that it is currently economically viable. And then I'll go through a couple of factors that would make thorium cheaper than uranium. First and foremost, these molten salts have a very low vapor pressure, so they operate at room temp or atmospheric pressures, even though they're at super high temperatures, so you have better thermodynamic efficiency. And so you don't need a reactor pressure vessel in order to keep it in. This simplifies your reactor by an enormous amount. You don't need extensive networks of plumbing and 9-inch steel plates and incredibly complicated things that are very hard to fabricate, very expensive. It's what drives the cost of your reactors up so much. Also, because it's a fluid fuel, you continuously refuel it and take out the fission products. So ideally, you would never need to shut down, probably a few times. But in general, there's no reason why you would have scheduled shutdowns. The scientific proof, this has all sounded like a big scientific dream, kind of like thermonuclear fusion, but I'd like to display how this has actually been achieved. There was 2 reactors. The first one was much smaller, so I focus on the second one, operated at Oak Ridge National Labs, called the Molten Salt Reactor Experiment, operated from 1965 to 1969. It was actually designed to help build a nuclear-powered aircraft, which sounds insane, but the positive side of that is that they built this beautiful machine, and it functioned for 4 years. It functioned at 7.4 megawatts of thermal power, and there was no major operational concerns. There was small hiccups in the design and actually getting the salt to flow and stuff, but it was the first time they'd ever done this on a massive scale, and they never encountered a problem that they couldn't overcome with minor fixes to their design. The bottom line after 4 years of that reactor's power is that 6,000 full power hours at 7.4 megawatts were achieved. And it proved every purpose that I've talked about. It proved passive control of the reactor through thermal expansion of the fuel. It proved the freeze plug feasibility. The incredible thing about this is classic nuclear engineering, you never shut your reactor down because it takes incredibly long to bring it up and it's really complicated. These guys, when they went home for Christmas break, would literally shut the reactor down by turning off their freeze plug, drain the reactor, they would come in a month, melt the salt again, pump it back into the reactor, and start up. It's literally less than a day process. It's fast and easy. And they also demonstrated the closed thorium fuel cycle. They irradiated thorium, turned it into 233, and then fueled the reactor with 233. Every main scientific prospect that I've talked about today was demonstrated by this reactor. So I'd like to sum up my talk with going back brief over all the major bullet points that I talked about, whether or not thorium is a perfect scientific energy source, little to no emissions or byproducts. I can never say as a scientist there would be no byproducts. There are radioactive wastes that are hazardous for up to 300 years. However, most of those are exotic metals that can be readily used and are employable by our society. And 300 years, we have vitrification technologies in order to turn it into a glass, and it's definitely safe over those timescales. So I'll check that off as being a satisfied requirement. Quasi-unlimited supply with literally millions of tons of the stuff and 100 grams to satisfy your entire life. I think that's more than enough justification. Passively safe, this reactor has demonstrated 2 passively safe mechanisms that make it control itself. As a natural environment, you don't need to actively cool it, things that went wrong in Fukushima, Chernobyl, and 3 Mile Island. So I'll call it again that so far as past it. The economic competitiveness, because nobody's demonstrated this on a massive scale, I can't go out there and give you blank numbers of how much this costs per kilowatt hour. However, I can definitely demonstrate over thorough reactor analysis and engineering that it would be definitely cheaper to build such a reactor, and it can be built on a much more economical scale of smaller 100 megawatts and stuff than current nuclear power plants. So again, I'm going to make a bold claim and say that passes. And it is a proven technology. People have done this. It's been done in just not only the United States, smaller reactors in other countries have been built, but that's the best example. It's all the feasibilities and the reasons that the reactor was shut down have been overcome. For all intents and purposes, every major challenge has been proven scientifically. It's not just a so-called paper reactor or something that looks beautiful. And with that, I think I'd like to thank you for listening to me, and I hope you guys are excited about thorium. Yes?
I have a question. If thorium is a perfect energy source, how are you going to fly a jet fighter plane with it?
That was a really sketchy concept. The idea was the Navy had taken over with nuclear-powered submarines, and the Air Force wanted to maintain superiority. So they wanted to have planes that could fly continuously for 6 months at a time. And back in the Cold War, it really didn't matter what it costs. So they literally built not only the reactor, but also the jet propulsion systems. I've seen them in Idaho National Labs. They're not quite the size of this building, but probably a third of it. They're like 75 feet tall and huge, insane cubes. And they built them and literally proved it would possibly work, although it was never built as a plane.
So a plane that's a big building size?
About the size of the Spruce Goose, if you're familiar with that. Howard Hunt's plane, or Howard Hughes' plane, is 300 feet wingspan. Yeah, enormous. Yes.
Why
is there a different reason that we didn't continue the work in the 60s as to why we don't implement it today?
In the 60s, it was politics, and then it kept going through the 70s at small and decreased funding levels. And then in 74, Carter ended reprocessing because India exploded a nuclear bomb on reprocessing fuel. Thorium has to have reprocessing in order to separate the 233. And so that killed it until Reagan, and then by then the science was dead. People had moved on to other projects. But it is definitely coming back. There's many groups in the United States and many across the world that are trying to do this.
Reprocessing is still illegal, right?
No. Reagan actually ended the ban on reprocessing, but it's not economically competitive.
Okay.
And the hoops are such that it's, for all intents and purposes, not easy to do. Thank you.